Give me 40 minutes. Just 40 minutes, and I will make Docker click for you. Forever. You know the feeling. You have 10 tabs open, you're trying to fix that one bug, and Stack Overflow gives you 5 different answers, and of course they all contradict each other. You finally get it working, you push the code, and the senior dev messages you, "It doesn't work on my machine." This is the single most frustrating problem in software development. And Docker was built to destroy it. The terms you've heard, they are the standard toolkit. You've probably seen this list: Dockerfile, images, containers, volumes, Docker Compose, port mapping, networks, and registries. By the end of this video, you will understand every single one of these terms. And not just in theory. No. You'll understand them in practice. Now, here's a quick look at the core concepts we're going to cover. You can see them in this table. Don't worry about memorizing all this right now. We're going to walk through it step by step. But this is our roadmap, from images, which are like blueprints, to containers, the actual running application. So how are we going to do it? We will take a simple Python script, a very basic one, and we will turn it into a portable, reproducible, multi-service application that can run anywhere. No magic. Seriously, none at all. Just a powerful system you are about to master. Ready? Let's begin by building our first portable application blueprint, the Docker image. Let's get our hands dirty. We're going to start with a very simple web app. First, create a folder on your computer named my-app. Inside that folder, we only need 2 files. That's it. First up, the application itself, app.py. As you can see, it's a basic Flask application. We import Flask, create an app, and define one single route. And what does it do? It just returns a simple greeting, hello, from inside a Docker container. Second, we need to list its dependencies. We'll put that in a file called requirements.txt. And for this app, there's only one. Flask equals 2.2.2. Now, to run this normally, you'd need the right Python version installed on your machine. You'd have to remember to pip install the requirements, and this is where the chaos begins. The core problem we're solving is the classic "it works on my machine" disaster. Believe me, this simple setup is a ticking time bomb. The moment you share this code with a colleague or try to deploy it to a server, it will fail. I guarantee it. Here's why. First, wrong Python version. Your laptop has Python 3.9, but the server, it has 3.7. Your app breaks. Second, missing dependencies. Your colleague pulls your code but completely forgets to run pip install. Your app breaks. And the worst one, conflicting dependencies. The server already has another app that needs Flask version 1.0, but you need version 2.2.2. Now, everything breaks. This, my friends, is dependency hell. The solution is the Docker image. A Docker image completely solves this entire problem. It's a single read-only blueprint that packages everything your application needs to run into one single portable file. Think of it like a perfectly configured frozen mini computer. It contains everything. First, a minimal operating system. Yep. Second, the correct language runtime. In our case, Python 3.9. Third, all the required libraries like Flask 2.2.2. And finally, your application code, app.py. Because everything is included, an image that works on your machine will work identically on any other machine that has Docker installed. So how do we create this magical blueprint? We write a recipe, a very special recipe called the Dockerfile. Back in your my-app folder, create a new file named simply Dockerfile, no extension. Let's walk through this recipe step by step. Step 1. From Python:3.9-slim. This is our starting point. Every image starts from a base image. We're telling Docker to begin with a minimal Linux environment that already has Python 3.9 installed. Step 2. Workdir/app. This sets the current directory inside the image for all the commands that follow. It's just like running cd/app. Step 3. copy requirements.txt space dot. This copies just the dependency file from your machine into the image. Step 4. Run pip install -r requirements.txt. The run command executes a command inside the image, but during the build process. This is where we install Flask. Step 5. Copy space dot space dot. Now we copy the rest of our application code, like app.py, into the image. And finally, step 6. cmd and in brackets python, app.py. Now listen closely. This is not run during the build. This is the default command that will run automatically when a container finally starts from our image. Now for a pro tip. The secret to fast builds is caching layers. Each command in your Dockerfile, from, workdir, copy, run, it creates a distinct layer. You can see it in this diagram here. The image is just a stack of these layers. Now here's the magic. If a layer's content hasn't changed since the last time you built, Docker doesn't rebuild it. It just reuses the cached layer from before. This is why we copied requirements.txt before we copied the rest of our code. Think about it. Your dependencies, like Flask, change very rarely, but your source code, your app.py, you change that all the time. So if you only change your Python code, Docker reuses the cached layers for the operating system, the workdir, and even that big pip install step. Your rebuild becomes almost instantaneous. It's brilliant. Enough theory, let's build it. Open your terminal, make sure you are in the my-app folder, and type this command. Docker build -t my-app :1.0 space dot. Let's break that down. Docker build is the command to build an image. The -t is for tag. This gives our image a human-readable name and version, like my-app :1.0. This is critical for managing your images. And that final dot, that's the build context. It just tells Docker to look for the Dockerfile in the current directory. When you hit enter, you'll see Docker executing each step from your file. You'll see it pull the base image, set the workdir, copy the files, run pip install, and finally export the finished image. You've done it! Seriously, you have successfully packaged your application and its entire environment into a single, portable, versioned artifact. Let's prove it exists. Type Docker images in your terminal, and you'll see it right there at the top. Repository my-app, TAG 1.0, a unique imaged when it was created and its size. You now have a portable blueprint.
But a blueprint isn't a house. It's just a plan on paper. Right now, that image is just sitting on your disk. It isn't running code. It isn't listening for connections. It isn't doing any work. We need to build the house and turn on the lights. We need to run our image as a container. This is the most important distinction in all of Docker, so listen closely. An image is the blueprint. It's a static, read-only file. A container, on the other hand, is a running instance of an image. It's the live running house built from the blueprint. And what's really cool is, you can create many identical containers from the same image, just like building a whole neighborhood of identical houses from one single blueprint. The command that brings our blueprint to life is docker run. Let's do it. In your terminal, type docker run my-app :1.0. When you hit enter, you'll see output like this. Serving Flask app, running on http://0.0.0.0:5000. It's working. The server is running inside the container. But now for the critical test. Open a new terminal window and try to connect to it. Type curl http://localhost:5000. And the output, curl, failed to connect to localhost port 5000. Connection refused. Wait, what? Connection refused? The server log clearly says it's running.
So why did this fail? This is the moment container isolation clicks. Your container is a lockdown isolated box. Look at this diagram. The app opened port 5000 inside the box, but there's nothing connecting it to your machine. It's totally sealed off. We need to create a tunnel. We need to explicitly map a port from our host machine to a port inside the container. We do this with the -p flag. The syntax is simple and powerful. It's -p, then the host port, a colon, and then the container port. So in our case, -p5000 :5000 means forward traffic from port 5000 on my machine to port 5000 inside the container. Let's try again. First, go back to the terminal where the old container is running and stop it by pressing Ctrl+C. Okay, this time I'm also adding the -d flag. This is really useful. It runs the container in the background or detached, so you get your terminal back. So for the action, run with port mapping. The full command is docker run -d -p5000 :5000 my-app :1.0. And the output you'll get is this long string of letters and numbers. That's your unique container ID. Now, let's access the application. In your other terminal, type curl http://localhost :5000. The output: hello from inside a Docker container. Success! The port mapping created the tunnel. As you can see in this new diagram, your request traveled from your host through the tunnel we made with -p and right into the container. It worked! Okay, so now that our container is running in the background, let's talk about your new control panel. These are the essential management commands you'll use every day. First, to list running containers, you use docker ps. This is your dashboard. When you run docker ps, you'll see a table with columns like container ID, image, command, ports, and names. As you can see in this example output, it's gold. It tells you everything you need to know at a glance. Second, to stop a container, you use docker stop. When you're done, you can shut it down using its ID or its name. And a quick tip, you only need the first few unique characters of the ID. So you could just type docker stop F4A5B6, and it works. And if you run docker ps again, the list will be empty. You're in complete control.
But we've also created a new problem. A huge problem.
The current development workflow is a nightmare. Think about it. Here's the cycle. 1. You make a code change in app.py. 2. You have to stop the old container. 3. You have to rebuild the entire image. And 4. You have to run a new container. This cycle is painfully slow. It completely kills your flow state. We need to edit our code and see the changes reflected live inside the running container without ever rebuilding. So what's the actual concrete problem here? It comes down to this. The container is a static copy. Remember that copy ... command in our Dockerfile? It took a snapshot of our code and baked it right into the image. The container is running that internal static copy. It is completely blind to the original files on your machine. When you change a file, the container has no idea. It's just chugging along with the old code.
So what's the abstraction that fixes this?
We need a portal. We need bind mounts. A bind mount creates a live two-way link, like a portal, between a folder on your host machine and a folder inside the container. It's you telling Docker, hey, for the /app directory inside this container, ignore the baked-in code. Instead, use the live files directly from my local project folder. As you can see in this diagram, we're creating a link. On one side, you have your local project folder on your machine. On the other, the /app folder inside the container. And the bind mount is this magic tunnel connecting them. Any change you make on your host is instantly reflected inside the container. It's beautiful. So how do we do it? The concrete solution is the -v flag. The syntax is simple. -v, then the path on your machine, a colon, and then the path in the container. And here's the magic shortcut for your current folder. Instead of typing out the whole path, you can just use -v $pwd in parentheses :/app. That $pwd automatically expands to your current working directory. It's a lifesaver. And a quick note for Windows PowerShell users, you'll use $curly brace pwd instead. Okay, action time. Let's run with a bind mount. First, make sure any previous containers are stopped. You can run docker ps and docker stop if you need to. Now the command, docker run -d -p 5000:5000. And here's the new part, -v $pwd in parentheses :/app. And finally, my-app: 1.0. The container starts up, but this time it's linked.
And now, for the aha moment, the magic trick. First, let's verify the initial state. In your terminal, type curl http://localhost:5000. The output should be, hello from inside a Docker container. Okay, normal so far. Second, open app.py on your host machine. In your editor, and change the message. Let's change the return string to, wow, live reloading is awesome, \n. Third, just save the file. That's it. Do not stop the container. Do not rebuild the image. Fourth, let's query the app again. Back in the terminal, curl http://localhost:5000. The output is, wow, live reloading is awesome! Success! Your code change was instantly reflected inside the running container. This is the fast development workflow we've been looking for. Now for a quick tip. You're going to hear about bind mounts and volumes, and it can be confusing. Let's clear it up. As you see in this table, there are two main types. The first is a bind mount. Its purpose is development, live editing source code. It works by linking a specific folder on your host machine. You manage it. The second type is a named volume. Its purpose is data persistence. Think databases, user uploads, things you can't lose. It works by creating a Docker-managed storage area. Docker manages it. We'll use these later. We now have a lightning-fast feedback loop. But real applications are rarely a single service. They have a web server, a database, a caching layer, a whole ecosystem of components working together. So let's level up. Let's split our app. We'll move the visit counting logic into its own dedicated counter service. This immediately creates a critical new challenge. How do two isolated containers built by us communicate with each other? Let's look at the concrete problem. Service isolation is total. By default, our My App container has absolutely no idea that a counter service container even exists. Without a network connecting them, they might as well be on different planets. As you can see in this diagram, they're just two separate, lonely boxes. So what's the solution? The abstraction we need is the Docker network. Think of it like a virtual private network switch. It's a space that we create. We can create our own custom network and then plug both of our containers into it. And once they are on the same network, something magical happens. Automatic service discovery by name. This is the key takeaway. Containers on the same network can find and talk to each other by name. If we name our container counter, our app can literally make a request to http://counter:6000. No IP addresses, no complex configuration. It just works. Okay, let's get our hands dirty with the concrete solution. This is a full end-to-end process. First, we'll create and build the new counter service. Second, we'll update and rebuild my app to call that new service. And third, we'll create a network and run both containers on it. Let's get it done. Step 1. Create the counter service. Create a new folder called counter service right next to your My App folder, so your project has two subdirectories now. Inside that new folder, we need a few files. First, counter service/counter_app.py. This is a very simple Flask app. It has a single variable, counter, which starts at 0, and it has one route, /increment, that adds 1 to the counter and returns the new number. And notice, this service will run on port 6000. Next, a simple requirements.txt file, just Flask version 2.2.2. And finally, the Dockerfile for the counter service. This should look very familiar. We start from Python 3.9 slim, set our workdir, posit our requirements, run pip install, copy the rest of our code, and set the CMD to run our Python app. Standard stuff. Okay, action time. Let's build the counter service image.
Navigate your terminal into the new counter service directory and run the build. The command is docker build-t counter service :1.0. Then cd ... to go back to the parent directory. Excellent. One service down, one to go. Step 2. Update the main application. First, we need to add the request library to myappsrequirements.txt. This lets our main app make HTTP calls. So add requests == 2.28.1. Next, we change the logic in myapp/app.py. This is the important part. We're ripping out the old counter logic. Instead, inside our hello function, we're now going to use the requests library. We'll make a request to the counter service using its hostname counter. The Docker network will resolve counter to the right container's IP address for us. So the line is response = requests.get and then the URL in quotes. And look closely at that URL, http://counter:6000. We are literally using the container's future name as its address. This is the magic. Okay, time for another build. Action, rebuild the main app image. Navigate into the myapp directory and run the build. We'll give it a new version. Docker build-t myapp :2.0. And then cd ... to go back up again. Step 3. Network and run everything. All the pieces are built. Now we wire them together. Here are the final commands. There are 3 of them. 1. Create the network. The command is docker network create my-app-net. 2. Run the counter service on the network. 3. Run the main app on the network. Let's break that down because those flags are important. For the counter, we used -- name counter. This is critical. We name the container counter so our other service can find it by that exact name. Then -- network my-app-net plugs it into our shared network. And for the main app, we do the same thing. -- network my-app-net plugs the main app into the same network, which is what allows them to communicate.
And now, the aha moment. The moment of truth. Action. See the services. Communicate. In your terminal, hit your main application's endpoint several times. curl http://localhost:5000. The output? Hello, this page has been visited 1 time. Run it again. Hello, this page has been visited 2 times. And again. Hello, this page has been visited 3 times. It works. This is undeniable proof. Think about the journey that request just took. Your request from curl hit the myapp container, which then made a second internal request to http://counter:6000. It got the count back and then sent the final assembled message back to you. 2 services working in perfect harmony. Now, for the curious among you, how it really works. This service discovery by name feels like magic, but it's actually just clever DNS. Under the hood, Docker runs a DNS server for each user-defined network you create. When your myapp container tries to resolve the hostname counter, Docker's DNS intercepts it and says, "Oh, I know counter. That's the container with the IP 172.19.0.3, and it returns that address." The request then proceeds as normal. You can actually see this for yourself. If you run the command docker network inspect my-app-net, you'll see a JSON output showing both containers and their IPv4 address. But using the name counter is stable and reliable. If you hard-coded that IP address and the container restarted for some reason, it might get a new IP, and your app would break instantly. The name is the contract. We now have a working multi-service application. But look at our startup process.
It's a mess. Step 1. Create the network, but only if it doesn't exist. Docker network create my-app-net. Step 2. Start the backend service with the right name and network. Docker run -d-name counter-network my-app-net counter-service :1.0. And step 3. Start the front-end service with port mapping and the right network. Docker run -d-p 5000 :5000 -name my-app-network my-app-net my-app :2.0. This is not a system. This is a list of chores. It's manual, it's error-prone, and it's brittle. There is a profoundly better way. And this involves a shift from imperative to declarative. With the old way, the imperative way, we tell Docker how to set up our app, step by step. But with the new way, the declarative way, we simply describe what our final application stack should look like. The tool that enables this incredible shift is Docker Compose. Docker Compose is the conductor for your multi-container orchestra. With just one command, it will read a single configuration file, build any custom images you need, create a shared network automatically, and start all your containers correctly. So let's get concrete. The solution is the dockercompose.yaml file. In the root of your project, you're going to create this one file, right alongside your myapp and counter service folders. Okay, let's look inside this file. First, at the top, we have version 3.8. This just specifies the compose file format we're using. Next is the most important section, services. This is where we define all our containers. First up, we have our main service, my-app. The build key, set to /my-app, replaces our entire Docker build command, and the ports key, with 5000:5000, replaces the -p flag. See how clean that is? Then we define our second service, the counter. Same thing, the build key points to the counter service directory. And here is the magic. The service name counter automatically becomes its host name. This file maps directly to our old commands. The Docker build command, that's now just build./myapp. The --name my-app flag, that's just the service key itself, my-app:. The -p port mapping, that becomes ports. And what about the --network my-app-net flag? It's automatic. You read that right. Networking is automatic. Compose creates a single private network and connects every service to it. They can immediately talk to each other using their service names, like myapp and counter, as their host names. The Docker network create command is gone forever. And now for the payoff. One command to rule them all. First, let's clean up our manual containers so they don't get in the way. You can find their IDs with Docker ps, then just stop and remove them. Docker stop my-app counter, and Docker rm my-app counter. Now, from the root of your project, run the command that changes everything. Docker compose up. For the first run, this will build both of your images, and pro tip, you can add a -d to run everything in the background. And here it is, the aha moment. You get the same result, but with an infinitely better process. Let's test it. The app should work exactly as before. Let's run the action, curl http://localhost:5000. And the output, hello. This page has been visited one time. It works perfectly. Our process is now simple, repeatable, and defined in a single file we can check right into Git. But here's the other half of the magic, the reset button. Docker compose down. This one command is your perfect reset button. It doesn't just stop the containers, it stops them, removes them, and critically, it deletes the network. It leaves your system completely clean. You've done it. Your entire stack is now defined in one file, launched with one command, and torn down with one command. Your application now works perfectly on your machine. But the entire promise of Docker isn't just to solve the "it works on my machine" problem for you. It's to solve it for everyone. Let's make it work on any machine. So how do you do that? How do you get this application from your laptop onto a production server? Or share it with a colleague? You don't zip up the source code and email it. That's the old broken way. Instead, you send them the pre-built, versioned image. That's the key. But here's the concrete problem we have right now. Your images are trapped. They only exist inside your computer's Docker daemon. If you look at this diagram, you've got your laptop with its Docker daemon, and inside you have myapp version 2.0 and counter service version 1.0. But over here, the new server, its Docker daemon is totally empty. If you ran Docker Compose up on that new server, it would fail instantly. It has no access to your images. So we need an abstraction. Think of it like this: GitHub for Docker images. An image registry is literally GitHub for Docker images. It's a central place to store and share your finished blueprints. As you can see in this flow, it's a simple two-step process. From your laptop, you do a Docker push to the registry. Then, from the new server, you do a Docker pull to get that exact same image. Simple. So let's walk through the concrete solution. Tag, push, and pull. Step 1. Get a Docker Hub account and log in. If you don't have one, just pause and go create a free account at hub.docker.com. Your username is your personal namespace. Once you have that, pop open your terminal and run docker login. It'll prompt you for your username and password. Okay, step 2. Tag your image correctly. This is crucial. To push to a registry, your image needs a fully qualified name. The format is always your username / your repository name / the tag. So let's do it. We're going to create a new tag for our existing image. Now, this command is cool because it doesn't copy the image, it just gives our existing image a second name, like an alias. The command is docker tag myapp : 2.0, and then your new name. For example, your Docker username / myapp : 2.0. Now, let's verify that it worked. Run docker images. And as you can see in this table, you'll now have two entries, myapp and your username / myapp. But look closely. They point to the exact same image ID. No data was duplicated, it's just a new label. Alright, step 3, push the image. Now we upload our blueprint to the world. The command is exactly what you'd expect. Docker push your Docker username / myapp : 2.0. When it's done, you can actually go to the Docker Hub website and see your new image repository right there. It's live.
And now, for the aha moment, the ultimate proof of portability.
First, we need to modify our docker compose.yaml file. Think about it. On a new server, you don't build from source code. You pull the pre-built image. So we need to change our compose file to reflect this. Inside the myapp service, we are going to remove the build line completely. And we're going to replace it with a new line. Image, followed by that full name we just pushed. Your Docker username / myapp : 2.0. We'll leave the counter service as is, so it still builds locally. Okay, step 2. Simulate a clean machine. This is the magic trick. To prove we aren't cheating, we are going to delete our local image. The command is docker rmi myapp : 2.0 space your Docker username / myapp : 2.0. This removes both tags and the image itself. If you run Docker images again, poof, it's gone. And now for step 3, run with Docker Compose. With the local image totally gone, let's run the command. Docker Compose up. Watch the output carefully. This is the moment it all clicks into place. The payoff. Look at that output. For the myapp service, it says pulling and then myapp pulled. Then for the counter service, it says building and counter built. And finally, both containers start. It didn't build myapp. It saw the image instruction and pulled it directly from the registry. You have now completed the entire end-to-end workflow, from local source code to a shareable, portable, and globally deployable artifact. This is the core loop of modern software. You code locally, you build an image, you push to a registry, you pull on a server, and you run the container. Then you go back to coding and the loop repeats. You've done it. Let's look at the powerful, repeatable system you just mastered. We started with just a few disconnected source code files, and now you have a complete multi-service application that can be launched anywhere in the world. This wasn't a random collection of tips. It was a methodical process, solving one concrete problem at a time. This is the workflow, the modern development workflow you mastered. Let's recap. First up, the Dockerfile. Using the tool Docker Build, you created the result, a portable, versioned image. No more "it works on my machine." Next, the container. You use the tool Docker Run-P And the result was an accessible, isolated application, alive and running. Then you created a bind mount. With the docker run-v command, you achieved instant code changes without rebuilding. That's your high-speed development loop. After that, networking. You use the Docker Network tool, and the result? Your services can now communicate by name. And then, Docker Compose. The tool was that simple dockercompose.yml file. The result was amazing. You can orchestrate your entire stack with one command. And finally, the registry. With Docker Push, you were able to share your images globally.
I'm going to tell you a secret.
The only difference between the simple counter app you just built and a massive application at Netflix or Google is the complexity of the code inside the containers. The workflow you just learned is the industry standard. The core principles are identical. 1. Define every service's environment in a Dockerfile. 2. Compose the entire stack declaratively in dockercompose.yml. And 3. Share the final immutable artifacts via an image registry. The image you push to Docker Hub is now the ultimate handoff. It can be run on a colleague's laptop, a staging server, or in a massive Kubernetes cluster. The fundamental work of packaging your application is done. You made a promise to me 40 minutes ago, and you delivered. You now have the foundational toolkit used by millions of developers every single day. You can confidently build, share, and run applications anywhere. Docker has now clicked for you. Forever.